Welcome to Topic 6, Unit 3, Continuity. We're going to start with an example. For this piecewise function f, find first the limit as x approaches 1 from the left. Well, since this has been graphed for me, I am going to just trace the function as we approach 1 from the left, and the y value we approach is equal to 2. Part B, the limit as x approaches 1 from the right. I will trace the graph as I approach 1 from the right, and I get the value -2. And finally, the question asks, what is the limit as x approaches 1 of f of x? Well, since the left-hand limit and the right-hand limit don't equal each other, the limit as x approaches 1 of f of x does not exist. A very important concept in calculus is the idea of continuity. So a function f is continuous at c if f is defined at c. So basically, if you evaluate f of c and you get a number, that you've met the first requirement. The second requirement is that the limit as x approaches c from the left has to equal f of c, and the limit as x approaches c from the right has to equal f of c. So basically, a function f is continuous at c if the limit as x approaches c of f of x exists and it equals f of c. Example 2, for the following functions, determine why the function f is discontinuous at a given point A on the graph. State which condition fails. So the first thing we always do is we evaluate f of c, or in this case f of a, and see if the function exists at that point. So for part A, I'm going to evaluate f of 2/5, and that's equal to the natural log of the absolute value of 5 times 2/5 minus 2. This becomes the natural log of the absolute value of 2 minus 2, or the natural log of 0. Well, 0 is not in the domain of the natural log function, so the natural log of 0 does not exist. So we're not continuous because f of 2/5 is undefined or does not exist. Part B, f of x equals 2x plus 1 when x doesn't equal -6, or x squared when x equals -6. And we want to see if this is continuous when a is equal to -6. So we'll start by evaluating f of a, or f of -6. Well, that means I'm going to plug it into this part of the piecewise function, and that's going to be -6 squared, which is equal to 36. And then next I want to see what the limit as x approaches -6 of f of x is equal to. Well, I'm going to get that by plugging -6 into the piece of the graph that is for everything except for -6. And I get 2 times -6 plus 1, which is equal to -11. So this is not continuous at x equals -6, because f of -6 does not equal the limit as x approaches -6 of f of x. Part C, we have another piecewise function, and we want to see if this is continuous at x is equal to 1. So first I'm going to evaluate f of 1. I get that by plugging into this part of the function because this is for when x also equals 1. So that is 1 squared, which is equal to 1. Now, because this piecewise function is defined differently to the left and right of 1, I have to evaluate the left and right-sided limits separately. So the limit as x approaches 1 from the left of f of x is going to be defined by this piece of the function because that is to the left of 1. And so this is equal to 3 plus 2 times 1, which is equal to 5. And let's evaluate the limit as x approaches 1 from the right of f of x. This is the part of the graph that's to the right, so I'm going to plug 1 into x squared and I get 1. So since the left and right hand limits don't equal each other, the limit as x approaches 1 of f of x does not exist. So that's why we're not continuous, because the limit as x approaches 1 of f of x does not exist. Example 3, use the graph to determine for each value of a, which of the three conditions for continuity are satisfied at x equals a and which are not. So when we look at x equals -2, we can see that we're not continuous primarily because f of -2 does not exist. Additionally, because the left and right hand limits do not equal each other, the limit as x approaches -2 also does not exist. At x equals 0, we can see that f of 0 exists. That is equal to 0. But the limit as x approaches 0 from the left is equal to 0, while the limit as x approaches 0 from the right of f of x is equal to 1. So we are not continuous because the limit as x approaches 0 of f of x does not exist. When we look at the point at x is equal to 2, we can see that f of 2 is equal to 1, and we can see that the limit as x approaches 2 of f of x, we are approaching 1 from both the left and the right. So at x equals 2, we are continuous because f of 2 is equal to the limit as x approaches 2 of f of x. Example 4, determine whether the piecewise function is continuous at x equals 0. Use the continuity test to justify your answer. All right, the first thing we want to do is evaluate f of 0. And f of 0, I get from this piece of the function that is equal to 1. Next, I have to evaluate the left and right hand limits because this function changes to the left and the right of x is equal to 0. So the limit as x approaches 0 from the left of f of x, I'm going to get when I plug into this piece of the function. So 2 times 0 plus 1 is equal to 1. Now I'm going to evaluate the limit as x approaches 0 from the right of f of x. I get that by using this piece, and that is equal to 1. So this means since the left and right hand limits both equal 1, I can say then that the limit as x approaches 0 of f of x is equal to 1. So finally, I can say that f is continuous at x equals 0 because f of 0 equals the limit as x approaches 0 of f of x. That's all for now. Thanks for watching.